Welcome, my name is Pritika and I will be teaching you exploratory data analysis today. We will start with defining terms, going over variation, talking about how do we visualize data, and we will go over some questions that you can ask yourself when you are doing data analysis, going over some extreme cases, outliers, going over how to handle missing values in your data, going over the different types of variables that you will run into. And then we're going to go over, lastly, some models, and I will give you some takeaways for this lesson. Sound good? Exploratory data analysis, or EDA, does not have a strict set of rules. Think of EDA as a state of mind. You're basically playing detective and investigating the ideas that you choose to explore. Some of these ideas will pan out and some of them won't. EDA is an important skill because you need to investigate the quality of your data. Data cleaning is just one application of EDA. You need to ask questions about whether your data meets your expectations or not. EDA is a fundamentally creative process. There is no rule about which questions you should ask and do research. Here are some key terms that we will define in this lesson. The first is a variable. A variable is a quantity, quality, or property that you can measure. An example of variable is the average rainfall in Seattle. A value is a state of the variable when you measure it. The value of the variable may change from measurement to measurement. For example, today there could be no rain, so it could be 0 centimeters. Tomorrow there could be 2 centimeters of rain. An observation is a set of measurements made under similar conditions. An observation will contain several values, each associated with different variables. I'll sometimes refer to an observation as a data point. Up here you can see a table of different categorical variables: temperature, humidity, wind speed, and this is an example of an observation. There's different values associated with each of these variables. And it's also an example of tabular data. Tabular data is a set of values, each associated with a variable and an observation. Tabular data is tidy if each value is placed in its own cell, each variable in its own column, and each observation in its own row. So let's start with what is variation. Variation is a tendency of values of a variable to change from measurement to measurement. Whenever you measure continuous measurements twice in real life, you get two different results. This is true even if you measure quantities that are constant, like the speed of light. Each of your measurements will include a small amount of error that varies from measurement to measurement. Categorical variables can also vary if you measure them across different subjects. Each variable has its own pattern of variation, which can reveal interesting information. The best way to understand the pattern is to visualize the distribution of the variable's values. Step 1 is to figure out if the variable is continuous or categorical. A variable is categorical if it can only take on one of a small set of values. For example, if your problem says there's only 3 options for the type of pet a person has, dog, cat, or bird, then that would be a categorical variable. A continuous variable, on the other hand, is one that can take on any value within a range. For example, your weight, your height. Your height can be 67.5 inches. That would be an example of a continuous variable. So, when we want to examine the distribution of a categorical variable, we use a bar plot. Like we see here, we are actually measuring the cut of a diamond, whether it falls in the categorical range of fair, good, very good, premium, or ideal. So now when we want to examine the distribution of a continuous variable, we use something called a histogram, as you can see in the picture. A histogram divides the x-axis into equally spaced bins and then uses the height of the bar to display the number of observations that fall within each bin. You should always explore a variety of bin widths when working with histograms, as different bin widths can reveal different patterns. In both bar charts and histograms, tall bars show the common values of a variable, and shorter bars show less common values. Places that do not have bars reveal values that were not seen in your data. Can you see any unusual patterns? What could explain them? So this is my favorite part of EDA, and that is asking myself these questions when I'm exploring my data. For example, in the example to the right with carat and count of a diamond, we can ask, why are there more diamonds at whole carats and common fractions? Why are there more diamonds slightly to the right of each peak than there are to the left of each peak? And why are there no carats bigger than 3? Now, let's talk about outliers. Outliers are observations that are extreme, unusual, and data points that don't seem to fit into the pattern. Sometimes outliers are simply data entry errors. Other times, outliers suggest important new science. When you have a lot of data, outliers are sometimes difficult to see in a histogram. The code below makes it easier to see with chord Cartesian. As you can see, this zooms into 0 to 50. Now, what do you do with outliers? It's good practice to repeat your analysis with and without outliers. If they have a minimal effect on the results and you can't figure out why they're there, it's reasonable to replace them with missing values and move on. But if you have a substantial effect on your results based on outliers, you should not drop them without justification. You'll need to figure out what caused them. For example, was it actually a data entry error? And disclose that you removed them in your write-up. The first way to deal with unusual values is to use the filter method. However, filtering is not the best method because just because one measurement is invalid doesn't mean all the measurements are. The second way to deal with unusual values is to replace those unusual values with missing values. The easiest way to do this is through the function mutate, and you can use the ifelse function to replace unusual values with a name. There's this example down below using R code and the mutate and ifelse method that replaces the unusual values with any values. If variation describes the behavior within a variable, covariation describes the behavior between variables. Covariation is a tendency for values of 2 or more variables to vary together in a related way. What does this actually mean? Let's take an example of covariation so you understand better. For example, we have hours studied to test scores. So how one kind of relates to the other. For example, as the temperature goes up, the number of ice cream sales also go up. The best way to spot covariation is to visualize the relationship between 2 or more variables. So now let's go over what a box plot is. A box plot is a way to display the distribution of a continuous variable broken down by a categorical variable. There are 3 elements of a box plot. The first is a box that stretches from the 25th percentile of distribution to the 75th percentile of distribution. This distance is known as the inner quartile range, or IQR for short. In the middle, there is a line that displays the median, i.e. the 50th percentile of the distribution, and these 3 lines give you a sense of the spread of the distribution, whether the distribution is symmetric about the median or more skewed to one side. Visual points that display observations that fall within 1.5 times the IQR from either edge of the box is known as outliers. A line or whisker that extends from each end of the box and goes to the farthest non-outlier point is the distribution. Here is an example of how a box plot looks. The function that we're using is ggplot in R, and we're using a built-in data set called diamonds, and we're using the cut as the categorical variable, whether it's fair, good, ideal, and we're using the price as the y-axis. So, to find the variation between two categorical variables, the goal is to count the number of observations for each correlation. Hold on, in this example here, we have two categorical variables. The first is cut of the diamond and the second is color. So as you can see here, we use geom count to find the count of how many number of observations for each correlation. The second way to go about finding covariation between two categorical variables is to use the count method. As you can see here, we import the data set and then we count the first categorical variable and the second categorical variable. Covariation goes beyond just the data set. We have to think for ourselves, what does this actually mean? For example, a positive relationship indicates that as one of the variables goes up, so does the other. A negative relationship means as one variable goes down, so does the other. For example, as the hours of studying goes down, so probably does the test scores. This would show a negative relationship. For actually visualizing the covariation among two continuous variables, we would want to use a scatter plot, and a way we can do this through R is to draw a scatter plot with the geom point function. However, if you have a larger data set, you have to change the way that you bin. Geom bin 2D and geom hex divide the coordinate plane into two-dimensional bins, and then you can use a fill color to display how many points fall into each of the bins. So now the fun part. You found a pattern. What's the next step? So it's important to ask yourself these questions. Could this pattern that I found just be due to a coincidence, random chance? How do you describe the relationship implied by the pattern? And how strong is the relationship actually implied by the pattern? What other variables could possibly influence this relationship? And would the relationship change if I just looked at an individual subgroup of the data? Models are a tool for extracting patterns out of data. To understand the relationship between cut and price without the confounding influence of carat is our goal. Since carat and price are so strongly related, they may overshadow the other patterns in the data, like how cut impacts price. So here we fit a linear model, LM, to predict log prices based on log carat. Logarithmic transformations are used to linearize the relationship between price and carat, as their relationship is often nonlinear. And this model captures the primary strong relationship between price and carat. By adding residuals to the data set, we can calculate the residuals of a linear model for each observation, and residuals represent the portion of price that's not explained by carat in the model. So the residual equals the actual log price minus the predicted log price. We use the mutate method to convert the residuals back to the original scale of price, since the model used logarithmic transformations. The third step is to visualize residuals. At scatter point, we use a scatter point geom plot, and the x-axis is carat and the y-axis is residual, which is the adjusted prices. So the purpose of this visualization is to show the strong relationship between carat and price has been removed, allowing all the other sub-tier relationships between, for example, between cut and price to become more visible. This plot explores how price deviates from what's expected based on carat alone. So points above the trend line indicate diamond prices higher than expected, and points below the trend line indicate diamonds priced lower than expected. By focusing on residuals, we can isolate non-carat factors that influence diamond pricing. So, in conclusion, there are 3 things I want you guys to walk away from this lesson with. Number 1, EDA is a fundamentally creative process. There's no rules about which questions that you want to ask and explore further to guide your research. Number 2, The best way to understand patterns is to visualize the distribution of the variable's values. And the best way to do that is to understand the type of variables. The best way to understand the pattern is to visualize the distribution of the variable's values. And you can do this by figuring out whether that variable is a categorical variable or a continuous variable. That's the end of this lesson. Thank you for watching. I hope you learned a lot. And thank you to Statistics Without Borders.